Thank you very much, Siri, for the organization of the summer school and of course, for inviting me to give a series of lectures. So we have 4.5 hours together, and I'll try to, it's both a long time to speak about one thing and a short time to speak about many things. I'll try to balance energy and entropy. And what I want to do is to give you, I will be speaking about active matter, which is the field in which I've been working for the past 10 years or so. And I want to try and give you a flavor of what statistical physicist people try to bring to this field. The outline will be a very brief introduction to active matter using slides. I will go back and forth between slides and backboard, again, to be able to cover as much as I can and still try to be pedagogical from time to time. And I will discuss mostly two main collective behaviors that you can see in active systems. Is how can you get condensed matter without cohesive forces, something that's impossible in passive equilibrium systems, and I will explain what I mean by that. And then I will discuss collective motion in a very simple setting, which hopefully will be a kind of introduction for the second part of these lectures that Bertrand will be giving after me during the week. Okay, so active matter is part of non-equilibrium physics, and there's a very nice sentence by Nicolas Ulam, who said that nonlinear physics is like non-elephant biology. And you can say the same thing about non-equilibrium physics, and what it means is that if I tell you that a bacterium, a theoretical physicist, and a tree are all part of the non-elephant biological world, I make a true statement, but we are so different from elephants that there is no hope that you'll make a unifying theory that says a lot about both myself, a tree, and a bacterium. It's the same thing about non-equilibrium physics. It's something that's ill-defined because there are many, many ways of not being in equilibrium. You could not have a steady state or not reach it. You could have a steady state, but it might not be given by the Boltzmann weight. Or you could have a steady state given by the Boltzmann weight, but you have orthogonal forces that violate tensorial symmetry in the steady state. And so you can violate any of these conditions and fall outside the equilibrium world, but you will do that in so different ways that if you want to develop informative theory, often what you have to do is you have to identify coherent subclasses and try to say something smart about them. So here on the left, you have probably something that has attracted most of the effort of the community for the past 50 years, which is the physics of glasses, which are systems which have a bulk dynamics, which is a bona fide equilibrium dynamics. They would, if you give them the time, relax towards their steady state, but that time would be more than the edge of the universe, and you will never see them reach their equilibrium. The second example, which also has attracted a lot of attention, is that of boundary-driven fluids. So this is paint mixed with acetone. When you remove the peel, the top layer, acetone starts to evaporate. It cools down the top layer. You have a gradient of temperature across the fluid, and it triggers at the macroscopic scale these fascinating Rayleigh-Bédard convection rolls. So here, if you look at what happens in the bulk of the fluid, nothing interesting is happening in the bulk of the fluid. It's bona fide equilibrium Hamiltonian dynamics, but yet at the macroscopic scale, you see something very interesting because of what happens at the boundaries. And active matter seems something a bit crazy to study because you have all types of problems. Here, you have a collection of agents, of units, each of them being driven strongly out of equilibrium. The very existence of steady state is not guaranteed. It's clearly not time independent. It will be driven by injection of energy. So this sounds like something very complicated to study. And yet what the past 2 decades have shown us is, in a way, not only is the phenomenology of these systems quite richer than many of the phenomenologies we've encountered so far in non-equilibrium systems, but it's also much easier to study. And the community has been able to make a lot of progress. And so I would like to try, and so many different types of people have contributed to that: experimentalists, fluid mechanics people, stat mech people, applied math people. So I will give you just one perspective, which is my own, on this field. Okay, so first let me start by kind of definition. What is active matter? As I told you, it's something that's best defined at the individual unit level, but contrasting with what an equilibrium dynamics is. So let's look at a silica bead in water, and let's look at its dynamics. This is a macroscopic object, so it's classical mechanics. And so you write Newton's equation of motion. So you have the mass times the acceleration. That will be minus the gradient of some external potential. And then you have interaction between these particles and the surrounding fluid. And if you take a micrometric bead, you'd have 10 to the 12 water molecule that all would be hitting this silica bead. And you can split the interaction between the fluid and the bead in two parts. There is an average part here, minus gamma v, which is a friction force, what we call damping. It's the drag. And what we know is that it opposes motion. So if the colloid goes to the right, then on average, what the fluid does is exerts a friction at low speed. It will be linear. And then, because every time I do my experiments, the position of these water molecules can fluctuate, I also have fluctuations around this average force. And this is the thermal noise that we model using Gaussian white noises. And so something which is interesting in this division is that the drag, if you look at the evolution of the kinetic energy of the particle, is responsible for dissipation of the energy, while the fluctuations are responsible for the injection of energy. Because these two terms come from the same equilibrated fluid, they are not independent. They satisfy what's called the fluctuation-dissipation theorem, which in this case takes the form of a relationship between the diffusivity, the temperature, and damping. This has important consequences, and in particular, it tells you that you can do stat-mech with n equal 1. When you learn about stat-mech, you're told that it only applies when you have a very complicated system. Here, I have a single colloid, but because of its interaction with the fluid, it inherits the equilibrium nature of the fluid, and its own steady state will be described by what's called the Boltzmann weight. So the state probability is exponential minus beta times the potential. So that's, in a nutshell, the equilibrium Langevin equation, and so that's not what I want to talk about. What I want to talk about is active matter. And so the question is, how do you go from that to something that's active? And you just have to do one thing. You have to dissipate energy and convert it into mechanical work. So if instead of looking at a colloid, I now look at a bacterium, the bacterium has flagella that it can rotate, and it can exert a force on the fluid. So there is a reaction force from the fluid, which I denote here as Fp, and so I have a new term that enters this equation. And this term is again responsible for injection of energy, because typically you move in the direction in which you're pushing. And so you've disconnected the injection of energy and the dissipation, and you don't have a fluctuation dissipation theorem. The system is driven out of equilibrium. Now, it's not completely clear whether just adding another random force here in addition to this random force there should change completely the physics of the system. So you can play a game. You can take a single particle in a quartic potential, and you can go from Hamilton's equation to my active matter equation. So I start with Hamilton's equation of motion. My particle oscillates in the well. It's doing closed loop on the energy surface in phase space. Then I turn on damping. And when I do that, I lose energy. I dissipate energy. So I fall at the bottom of the well. And then I turn on the Brownian noise. And so you have fluctuations around the minimum of the potential, which correspond to these loops here in phase space. And essentially, these loops here will create something that will be exponential minus beta x4 over 4 here in the center. And then I will turn on an active force that can be +1 or -1, and that will stochastically change between the two. And what you see is that when Fa is positive, suddenly my particles self-propel until the trap force balance its active force, and then when it flips, it goes on the other side. And so you see that this simple modification of adding this persistent force has brought a very strong difference on the steady-state distribution. So already at the single particle level, these active dynamics are much more complicated than the passive ones. Now, if all there was to active matter were weird one-dimensional stochastic equation of motion, the field would not be very interesting. But what's interesting is when you take many of these particles and you put them together, the type of collective behavior they have access to. So the idea is that because each particle is running out of equilibrium, the system is strongly out of equilibrium, much more strongly than other classes of systems, and that can lead to new physics. So here I'm showing you 3 snapshots which represent quite well where our field was 20 years ago. Almost everything in biology is active, from molecular motors to animal. And so these systems were initially strongly motivated by biological systems. So on the right, you have pictures from an experiment of what happens if you cut your skin and you look at the wound healing. So you both have cell division and cell motility, and so you have invasion of this empty space here by the cells, and you see that they do this complex dendritic creation. In the center, you have the flight of starlings, as studied by the lab of Irene Giordina and Andrea Cavagna in Roma, and they do this kind of crazy motion in the sky. And on the left, there is a very nice experimental system developed in the lab of Nikta Fakhri. So these are starfish oocytes. They are swimming, they're rotating, and they're swimming upward. So here what you see is the surface of a fluid. The oocytes are swimming upward. So because they are pumping water downward, there is an attractive force between them.
What is an oocyte?
An oocyte, an ovocyte, an egg. Yeah. So these attractive interaction between the oocytes lead to this crystal. But because each of the oocytes is rotating, this crystal has a crazy dynamics, and you'll see at some point it starts rotating uniformly. So this formation of rotating crystal is something that had been seen also with bacteria that do the same thing. But if you look closer to the crystal, in addition to the global rotation, you have these odd elastic waves, these very complex excitation that you see here of the crystal, which are things that had never been seen before. So there is a whole new zoo of phenomena that you see in biology and that people are trying to model with these active matter models. Thanks, Gerard, for the question. Please interrupt me anytime I say something you don't understand, and let's try to keep this as informal as possible. I have a program, but if I don't reach the end of the program, it's not a big deal. Okay, so 2 reasons why the field attracted a lot of people. The first one is biological relevance, because almost everything in biology is active. And the second one is just new dynamical phenomenology. So if you've been working in statistical mechanics, it's because you love collective behaviors. If you have new collective behaviors, you're happy. And so people like me join this field because of seeing all these type of movies. But over the past 10 to 15 years, the field has changed, because physicists and chemists have been able to engineer synthetic particles, which at the microscopic scale are being to be active. And that paves the way for biomimetic materials that could be able to change shapes, to spontaneously heal. And so there are tons of exciting applications over there. So here on the left, you have self-propelled colloids, which forms these clusters without attractive interactions. On the right, you have self-propelled droplets that form these filaments that continuously bend and merge. And my favorite is the one in the center from the lab of Denis Barthelot, which is about how colloids can swim together. So these are active colloids. They go in the random direction. They interact via electrostatic and hydrodynamic interaction. And you see here that you have a flock of colloid that is swimming spontaneously to the left. There is no global field to the left. It's spontaneous symmetry breaking. If you were to redo the experiment, you would see it to the right. So the first part of my lectures will be about that, and the last part of the lectures will be about this. Okay, and so what's the approach that people in StatMech have developed? Essentially, it's to do micro to macro study of simple models, and then to try and test their generality and see if we can connect with these experimental systems. Okay, so that's for my introduction. And now we'll turn to the first part of these lectures, which will be about the emergence of dense active matter in the absence of cohesive forces. Are there questions so far? No? Okay, so let me give you a crash course on what should we expect if we take an equilibrium system that does liquid-gas phase separation and to which we add self-propulsion. So in systems which are in equilibrium, the most probable macro state you observe is set by doing a competition between energy and entropy to minimize the free energy. If you have attractive forces in your system, minimizing the energy favor cohesion. Right? If you are all pulling on each other, you're happiest when you're making a big cluster in the center of the room. But then I have a lot of information on where you're in the room, so your entropy is very low. And on the other hand, if you're just running around and spread uniformly, I have very little information about where each of you is, and so your entropy is maximal. The free energy is the energy minus temperature times the entropy. So as I vary the temperature, I will vary the respective weight of energy and entropy in selecting the steady state. So at high temperature, energy dominates, and so I want to favor the disorder, so I expect to see a uniform fluid and a gas, entropy. And as I lower the temperature, energy will dominate, and if I have a conserved total mass of particle, what I will see is liquid-gas coexistence. Okay? Now imagine that you are my equilibrium colloids, you're doing random walks and hugging each other, and you've made this nice crystal in the center of the room, and I ask you to start walking. Well, initially, you have strong arms and you're just walking slowly, so the cluster will just jiggle a little bit around. Maybe some of you will evaporate, but you expect that the cluster will hold. And then I ask you to run. And when you run, suddenly you'll break apart. So what is natural to expect is that as you increase activity, you should be able to vaporize a cluster. So this is a simulation of equilibrium particles interacting via a potential which has a hard core so that they cannot penetrate, but an attractive tail. So initially, the system is a Brownian dynamic, so there is no self-propulsion at a temperature in which this phase-separated cluster is stable. So if I simulate that, nothing happens. And then at some point, I will turn on a little bit activity, and you see that essentially not much happens. So maybe you see that some small gaps open in this big cluster, but not much change. I increase the velocity to 5. Okay, fine. You vaporized the cluster. That's exactly what we expected. I keep pushing the simulation. I go to 50, and then something bizarre appears, which is that there is a reentrance first transition, and the cluster forms again. So I can put that in a phase diagram. So my Lennard-Jones potential is this potential with repulsive hardcore and attractive tail. At zero self-propulsion, I have my liquid-gas phase coexistence, the equilibrium one. And as I increase the activity, I first vaporize my cluster and I get a homogeneous fluid until I have this reentrant phase transition into again phase separation. And the mechanism that allows to understand this is called motility-induced phase separation, and this is what I will be discussing in the next hour or so. Now, there is something quite remarkable about that, is that I can take this potential, which has repulsive core and attractive tail, the attractive tail that explain this phase separation, and I can redo my simulation without the attractive tail, so only repulsion. This is the phase diagram I observe. No phase separation here, but you see that the binodal, the coexistent density, have not moved at all. So this phase separation doesn't even need attractive forces to exist. Okay. And now what I want to do, okay, so that's what you see in a computer. That's also something which has been observed in experiments. These have been done in the lab of Joshua Shevitz in Princeton, where essentially it's a 2D surface of a petri dish on which you have bacteria. And as time goes on, they experience hardcore repulsion. And as time goes on, they do this big condensate that grows. And these are experiments with self-propelled colloids, which have been studied in the lab of Dick Arts in Oxford. Okay, so what I want to do in the next hour or so is to tell you why do we have this phase separation, what is the instability mechanism that allows to understand the emergence of this phase diagram, and then mathematically what controls the coexistent densities, how different is it from equilibrium? How do you build a theory for the phase equilibria of this type of system. And then I will come back to examples and discuss application to bacteria.
Yes. Self-propelled force, FP.
Yes.
So here you change its strength, but
Yes.
but it doesn't have a preferred direction. It's a random
It's
direction.
doing a random walk. So in this, okay, thanks very much for the question. Typically, there are a number of dynamics we look, but it could be, for instance, rotational diffusion. So you're doing a continuous random walk, or it can be this telegraph-like process where you change discretely. That's called run and tumble, and they give exactly the same type of result. Was there a question? Yes.
Yes. So inside the clusters and the passive equilibrium clusters, there
Yes.
seem to be more funky stuff going on with the gaps inside compared to in the MIPS cluster where it seems denser.
So the MIPS cluster is denser because that density is larger than this density. So that's the first thing. So they are more compactified because FP is compactifying. The dynamics of these gaps is interesting. So if you take equilibriumizing model at half the critical temperature, you have spins +1 and -1. You need to produce a magnetization which will be 0.6. So you will have gaps. And gaps like to be close to each other. So even in equilibrium, you expect to have bubbles inside your dense phases. Now, the dynamics of these bubbles becomes different when you have non-equilibrium systems, and lots of people have been studying this. I will comment on this at the end. I will not discuss that in detail here. But there could be parameter regime in which the distribution of size of the bubble is power law, with an exponent such that you cannot accommodate them. And so that as you would increase the system size, you would go from phase separation to a uniform bubbly liquid. Still controversial, so there is one paper that has reported that, but it seems pretty robust numerics. So the physics of this bubble is very interesting, but that's beyond what I will be discussing. Any other questions on this slide? Okay, so the big question is, if you have self-propulsion and repulsion, why do you get liquid gas equilibrium?
Yes. In the middle phase, the homogeneous one, which doesn't look a priori fun, but there must be some structure as well, some correlation, or
No,
is it because it's far from equilibrium.
It is, but it looks like a uniform fluid. So if you look at the structure factor, you don't see anything interesting there. Okay. No, there are modifications you can bring to the systems, making them anisotropic and stuff like that, where then the non-equilibrium nature becomes important. But in this isotropic one, I'm not aware of anything particularly interesting in the homogeneous phase. Okay, so I will turn that off for now, and I will go on the board. Can I have maybe a bit more light to... Thanks. Okay. Let me choose chokes. This is white. No, that's not white. That's yellow. Blue and green. And I have something burning in my pocket. Why are you burning? Okay, so let me start by looking at the instability mechanism. I cannot do anything about the quality of my handwriting, but I can do something about the size. Is this good? Large enough in the back? Okay, cool. I can do something about the color, but I need, okay, maybe yellow is better. We'll see. We'll see if yellow is better. I don't know. You should buy Hagoromo chocks, not that. Okay, so I imagine that green is also horrible. Okay. Brown. Yeah, no. Okay, I'll go with yellow and white. Okay, so I will start discussing what I called pairwise forces, active particles, which I will call FAPS because I love acronyms, which is a collection of particles whose dynamics would be Brownian dynamics. So I have the speed of particle I is the mobility times the sum over particle J, particle J of grad V of Ri minus Rj. Then there's a minus sign. Then I have self-propulsion. And the angle of my particle is doing rotational diffusion. So eta is a Gaussian white noise. And because I want, okay, I know. So I have a bunch of interactions with all the people who are pushing on me, and I will call all these forces Fi when exerted on particle I. And what I want is to make a simpler model of this that allows me to understand what happens in the complicated system. So I imagine that I have my system and I have a density field that is varying over space. So there are some place where the density is small, and maybe other region where the density is larger and some gradients. And I have my particles which are doing their rotational diffusion motion. Okay, so they are going for some time, and then they can enter this other regime where they would go slower. And essentially, what I'm going to say is that the density field rho of R varies on a large scale. And so it takes a lot of time for the particle to go from a dilute region to a dense region. And whenever I'm in this dilute region or dense region, I don't believe that the structure has so much to do. So this force here, I can average it. And to do that, I will rewrite it as follows. I will say that Ri dot, I can take this force and look and split it between the part projected along Ui, U of theta I being the orientation of my particle. So if I have a particle here, this is Ri, and this is theta I. And then I also have a part which is orthogonal to the particle, so which will be Fi minus Fi U of theta I times theta I times U of theta. I haven't done anything in my equation. I've just added and subtracting the projection of F along Ui. But now I can do something else. I can say that, well, this on average, if I'm going in this direction, there is no reason why you would push me more to the right than to the left. So the average, so this average here, so this is parallel to U perp of theta I. And on average, it will be 0. So it's really a kind of noise. Now, this term here is a kind of effective self-propulsion. It's how fast I'm running in the direction which I'm looking, given that you're pushing on me. Most of the time when you run in a crowd, you collide with people in front of you more than people behind you. So this, I can average it, and I can say that this is essentially a self-propulsion speed that depends on the local density times U of theta I. So what I'm saying is that a particle in this crowd is essentially experiencing a speed V of rho times U of theta I and experiencing a noise. And when I'm doing that, I'm doing a kind of mean field approximation, saying that I'm randomizing over all collisions I can do. Now, what we said is that rho of R varies on a large scale. And because it varies on a large scale, it also varies on a long time. Because To make rho relax, you need to transfer mass from one place to another, and this takes time. Okay, so if I have a modulation of rho of x, which is over a scale L, the time it will take for mass to move of this distance L will diverge with the system size. So my relaxation time scale as L to some power, where z is a positive exponent, would be 2 if the system is diffusive, 1 if it's ballistic. And in particular, it's much larger than 1 over dr, which is the relaxation time of these dynamics. All right, so if I look at the average of u of theta of t, u of theta of 0 t, this is exponential minus dr t, and so you get a relaxation time, which is 1 over dr. And so it means that for all purpose, when I have my, bye-bye, I don't know how I'll get it back, but hopefully I can get it back at some point. So that's fine. Yeah, I'll do that. For now I'm fine. Okay, so essentially, if I'm interested in short-time relaxations, I can look at a simpler problem. Instead of looking at V of rho of r, I can assume that rho is frozen. It didn't have yet the time to relax. And so this is just a non-interactive problem for a single particle in a field which is not homogeneous in space. And that's a one-body problem which is easy to solve. And so we'll start by looking at this one. Yeah, also kiss goodbye to my chokes.
There's some sticks there, I don't know.
Yeah, I know. I'll be fine. Space varying. Okay, I don't know how many chokes I'll break. Space varying speed. Spatially varying speed. So how do I study the dynamics of my particle in space varying speed? I can write down the master equation, the Fokker-Planck equation that correspond to this coupled Langevin equation. So if I call P of R theta t, the probability density to find the particle at position R, angle theta at time t, I will have one part which is a transport part, which is due to my first equation with a V of R. So I'll get V of R u of theta p. And then I have the dynamics on theta that give me plus dr d theta p of r theta. Here I'm doing it in 2D. I could do it in 3D. It would just be more unpleasant vector notation. It would be the same thing. Okay, and let's say that for sake of simplicity, I'm looking at R in a box of size L. Okay, so if I want to look at the steady state, actually this is very simple. So I set dTp equals 0, so I need to make the right-hand side vanish. I know what rotational diffusion is doing. Rotational diffusion is making things isotropic. So the first thing I can test is I can have an ansatz, which is that P of R theta is just, I should not call it P, I should call it Q of R. And then automatically this gives 0, but this doesn't. However, if I have Q here, if V times Q is a constant, I get the divergence of a constant vector field, which in space, which will be 0. So I can see that if Q of R is proportional to 1 over V of R, then I get minus div of V of R P plus dr d theta P equals 0. So I just have to check that I can normalize it, and if essentially V doesn't vanish So if kappa equal integral d to r 1 over v of r is less than infinity, then my steady state distribution, P steady state, is kappa over v of r. Okay? So why, what is this telling us? It's telling us that, so there is one thing which is very intuitive. If I'm doing a random walk in this place, if I go fast somewhere and slower elsewhere, you have a higher probability of finding me where I'm slower. So if you run, you expect that your steady state distribution is kind of proportional to 1 over v of r. It's not completely trivial that this is isotropic. It's not completely trivial, it should be, because grad v gives you a direction, so it could have played a role, but it turns out it doesn't. And so the take-home message, and this is very robust to many types of active dynamics, is that active particles accumulate where they go slower. So that will be fact 1. No, it should be fact 2 and fact, okay, yeah, fact 1. Fact 2, what we know is that repulsive forces essentially behave as v of rho of r. And as I told you, if you run in an empty corridor to catch your subway, you run faster than if you collide in people. So what you expect is that the variation of your speed with the average density is negative. It's actually been measured in numerical simulation by Yao and Philly in 2012. And what they found was that if I plot the average speed of particle in a uniform system of density rho naught, I have essentially a linear decay with a rounding close to some density rho star. So what you find is that V is essentially V naught times 1 minus rho over rho star. That's numerical result. Okay, so we have two ingredients. Particles accumulate where they go slower, and they go slower where they are denser. What I want to show now is that this typically gives you a linear instability towards phase separation. Yes, Julien?
So which type of particles?
This is the one on top left. Yeah. I think that people have done that with harmonic repulsive potential, WCA potential, Yukawa potential. You get always the same thing. What happens here is highly non-trivial, the way you fall to zero, and important. But the linear decay at low density, it's a little bit trivial, because if you look at this guy, this will be proportional. The collision term will be proportional to the density. So the rho dependence, you expect it from mean field argument. Yes?
And then there is no lower bound for the velocity, the density can be infinite?
So if you have soft repulsive potential, yes. If you have diverging potential, at some point you expect that there is a cutoff, or something that you never reach. In principle, Lennard-Jones, you can contract as much as you want, but just that your energy shoots up. So in practice, in simulations, as you saw in the movie I showed, you don't see any overlap if you use numbers of order 1 for your velocity.
Yes. You said repulsive forces are. So what does it mean? The precise statement.
Okay, so the precise statement is if I want to define a V of rho, I will define it as the average of. Where is this? I wrote it somewhere. The one I have on the top. So it's V naught plus Fi scalar product Ui, averaged in a homogeneous system at density rho naught. Okay, so I prepare my system at density rho naught. I run my simulation and I measure that, which is how fast you go along the direction you're pointing. And if I plot it, I see that. And the way you can understand it is because if you're running in a crowd of particles, you have more collisions. I mean, the V1 minus V2 is larger, ahead than behind. So the collision rate is faster with people in front of you. The other way of saying is that the pair correlation function has a peak in front of you. Okay. And that leads to this slowing down.
So it's not directly a force in the potential V. It's dynamical force,
so
or an interpretation of the.
So if you go from the top left, okay, this is exact. This is exact, right? I've just added and subtracted. Then it's a free country so far, so I can average this. I can say that on this side of the ocean. I can average this, and when I do, I can define this V of rho. And then the result is this. So here there is no approximation. There is an approximation when I say that I can replace these dynamics on the top by a dynamics in which I would have this on the bottom, which I will do, and it works fine for some things and bad for others. Okay. Make sense? Any other question?
A stupid one. So if they're non-reciprocal but still repulsive, I presume this holds, but just some average reciprocal repulsive force.
MIPS in non-reciprocal. Okay, so that's one of the non-reciprocal things which I think has not been tried. You would know.
What does reciprocal mean?
So if Fij is not minus Fji. So people right now are a bit excited with that because all these systems, they interact via mediated interaction. There is a fluid, there is some chemical, so there is no momentum conservation. So there is no reason why Newton's law should apply. I don't think it has been tried. I think as long as you have repulsion, I mean, you may change, the effective V of rho and stuff like that. But I don't think, I don't know. I haven't thought about it. That's a good question. Any other question? Okay, good. So why is this leading to an instability? Okay. Now, so I still like the red. So okay. 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 Yeah, no light here, right? No. Feedback loop. So imagine that you start in a system which is homogeneous. So this is, let's say, in 1D. So I have a density rho naught. I have, because of my interaction, some speed v of rho naught. And I assume that there is a fluctuation. Okay, there is a fluctuation. Density goes higher somewhere, lower elsewhere. Now, so this becomes, I should have done it in blue. Rho naught plus delta rho. Because I have a fluctuation of the density, I will get a fluctuation of the speed. So this will lead to a new speed, which is something that looks like that, which is V of rho naught plus delta rho of R, of X. And again, because I assume repulsive interaction, I have this V prime of rho naught, which is negative. Now, if delta rho is small, I can expand. And this is essentially V of rho naught plus delta rho of X, V prime of rho naught. As I said, there is a time scale separation between the relaxation of my one-body dynamics and my collective dynamics. So the one-body P of R tends to relax towards, I'm not saying it reaches it, but just it starts to relax towards 1 over V of rho naught plus delta rho of X. Okay, so what does it mean? It means that rho naught plus delta rho goes to okay, towards, no, sorry, I think I had called it kappa, the normalization constant, goes to kappa over V of rho naught plus delta rho, which is written here, and which I can rewrite V of rho naught times 1 plus delta rho V prime of rho naught over V of rho naught. Okay? Again, delta rho is small, so I can expand. I get kappa over V of rho naught, which is rho naught. And this 1 over 1 plus becomes 1 minus delta rho V prime, yes, of rho naught versus V of rho naught. And now the question is, am I relaxing towards something that amplifies the fluctuation or something that damps the fluctuation? So I want to compare this, which is the target towards which I will relax, to that which is the starting point. And what I see is that if delta rho, the initial fluctuation, is lower than minus delta rho naught V prime of rho naught over V of rho naught, then the fluctuation is amplified. And this I can read what it means. I can rewrite this in a slightly nicer way. I divide by delta rho, I divide by rho naught, and I get 1 over rho naught plus V prime over V, which is negative. That's the derivative of log of rho naught plus the derivative of the log of V. So this is equivalent to the derivative with respect to rho naught of the log of rho naught V of rho naught, which is negative, which is equivalent to the derivative with respect to rho naught of rho naught V of rho naught to be negative. So you find with this argument a condition, which is that if rho times V is decreasing, then essentially you have a feedback loop that will be such that when you are getting a bit denser, you go slower, and you accumulate there, and then this keeps amplifying the perturbation. And this instability is what drives the motility-induced phase separation. So this instability leads to motility-induced. Yeah, maybe not. Motility-induced phase separation.
So this only works provided your unmatched for the local equilibrium won't be perturbed by this.
So, okay. So this is a hand-waving argument, and you could criticize the timescale relaxation, the assumption of having a V of rho and things like that. It works qualitatively fine to explain the instability. In some models, it works quantitatively very well. In the pairwise forces model, it does important quantitative mistakes because it violates a symmetry. Essentially, doing mean field is not a big deal, but we are doing it too early. I'm doing it at the level of particle. What I could do instead is write down an exact evolution equation for the density of particle. I would get something like a Boltzmann equation. Or no. And at this level, do a mean field closure, and then it would work much better. But it's much harder. It's much harder, and also it gives you a criterion that's very hard to understand, while this qualitatively works very well and is easy to understand. Yes?
Should we understand the velocity as a local temperature?
So it depends how you define temperature. So in a thermodynamic sense, no. These particles have a large-scale diffusivity, which is given by V square over dr. So they have a constant mobility. If you want to call d over mu a temperature, you can. But the mapping stops there. So you cannot, you cannot get a Boltzmann weight with an effective temperature. You cannot. So.
Are the physical mechanism similar to what you would have with an usual gas, coupling density and temperature?
There are differences. So momentum is not conserved. So you don't get the same thing as when you take So you have these granular media experiments with the. So it's not the same. It's not the same set of equations. It's not the same instability. No, when you have granular media. There is this picture by Deftkoloze and others that dissipation, collision leads to dissipation, which lowers the temperature, which leads to enhancement of the probability, which is not very different from that. What I will show you now is how you account for the phase equilibrium and the nonlinear profiles. And I've never seen that done for the granular gases, but this is something I'd like to know. How much of the mathematics of what I'm going to do next changes if you add momentum conservation. But yeah, Any other question before we dive into?
Just one more.
Yeah.
V is signed here?
No, but I mean, in principle, if V could become negative, right? If I'm moving in that direction, V of rho, and you're pushing myself back, it could be. But V is, if thought as to be V naught is your self-propulsion speed. Now V of rho can change sign if people are pushing on me faster than I'm propelling. Okay, so what I've done so far is essentially linear instability. I'm looking at a small delta rho will trigger a feedback loop that will take me toward a non-uniform state. However, I've not respected the title of this conference, which speaks about nonlinear dynamics, and so we want to go beyond linear stability. And essentially, if this leads us to having the coexistence between particle and a droplet, we want to understand how this phase equilibrium is set. In particular, in the movie I showed you, we started with phase separation, then we had homogeneous fluid, then we had phase separation, but it's not clear if these two phase separations are the same thing. In equilibrium, you know that phase equilibrium is set by equating chemical potential and pressure. What about here? Do we have chemical potential? Do we have a pressure? Are they equal in coexisting phases? So I want to try and go there, and this is what I will be doing now. How do I erase? Oh, that's nice. Okay. It's a whirring sound. Okay. So, what I want to do in the next half an hour is to understand phase equilibria in scalar phase separated system. So I will start with a reminder of the equilibrium case, and then we will see how we deviate when we have this system. The idea is we have, particles that are a bunch of positions, and we can define density fields, for instance, by doing some kind of empirical measure. And we can coarse grain them. And at the hydrodynamic level, what we expect is to have a mass conservation equation, dt rho of r, t, will be minus the divergence of a current. And what we know is that this current in this phase separated system, because the M is isotropic and there is no way of spontaneously breaking a symmetry, we know that J vanishes in uniform states. And what this means is that J, which has to be expressed as a functional of rho, has to have gradients inside it. And so what I can do is I can look at a class of system such that J of R and rho can be written as a mobility that can be also a function of R and rho. And then with a minus sign, the gradient of some mu that will be also a function of R and rho. This stage, this is pretty general, but to make progress, what you can do is you can say, well, I'm trying to do a harmonic equation, so I will do a gradient expansion of mu. So, and I should not call this mu, I should call this G, sorry. So I do something a la Ginzburg-Landau, and I say, well, G of R, which is a functional of rho, in a gradient expansion, there is a local part, G naught of rho of R, and then there'll be gradient term. Symmetries prevent first order gradient, but I can have second order gradients. And so I will say I have minus kappa of rho Laplacian rho, and plus lambda of rho grad rho square. As a sanity check, we can check that we recover, and then there would be plus order grad force.
Sorry, what about 1 over n factor in empirical measure?
It's just a normalization. I could put the 1 over n or not. It just changed the extensive, whether the field is intensive or extensive. That's not, that wouldn't change anything. Okay, so let's, as a sanity check, verify that in equilibrium we can. This is a good form. So we look at what's called the Canillard equation, which is the case in which G is the functional derivative of a free energy. G of R is delta over delta rho of R of a functional f, where my functional f is integral dr prime of some local free energy density, and then some surface tension term, C of rho of R prime over 2 grad rho of R prime squared.
Okay, so yeah. Just a question of notation. So theta and then false derivative means
order. So it's a calligraphic O, big O. I don't know. So I'm truncating after second order gradient. I will not need them. Okay, so if I want, so I have my free energy. I want to compute the functional derivative. When the functional derivative hits this integral, it gives me f prime. So I get that G of R is f prime of rho of R. Then when the functional derivative hits this guy, once it takes the derivative of C, so I'll get a C prime grad rho square over 2. And once it hits one of these grad rho. So we'll get a grad of a delta function, which I have to integrate by part, and then my gradient will again hit this C, and it will flip the sign. And so I get a minus C prime of rho over 2 grad rho square, and then minus C of rho Laplacian rho. And so I get that this has the good form, and I didn't do mistakes, good. And one of the things that you see is that this model on top, this is an equilibrium model only if kappa and lambda are of these terms. Otherwise, I cannot find a free energy such that G is a free energy. So this equation, which I will call equation 4, because that's what I called it in my notes, yeah, equation 3. So equation 3 is in equilibrium. if and only if 2 lambda plus kappa prime equal 0. Okay. And you can check that because you can generalize Schwarz theorem to functional derivative, and you would find that delta G of R over delta rho of R prime is not delta G of R prime over delta rho of R, which is the generalization to functional derivative of the Schwarz cross-equality theorem for vector fields. Okay, so I have a model which includes equilibrium phase separation, but contains more than that. And so the question is, how can we build the phase equilibrium for this model? So you see that the local part of G deals with essentially the free energy density, and these gradient terms are kind of generalization of a surface tension. So how do I construct the phase equilibrium? And I will first do it in the equilibrium case. We call phase equilibrium the value of the densities between coexisting plateaux. So I consider a phase-separated system in which I have a liquid droplet in the center and a gas phase around. And I look at an interface that goes through the system. And I consider macroscopic phase separation so that the curvature radius is, I assume, is infinite. So I assume macroscopic phase separation. Okay, so essentially if I plot my density profile rho of x as a function of x, I start in the gas, I have an interface, and I arrive in the liquid. So I have rho liquid here, rho gas there. I can define an abscissa x gas, x liquid. Okay? And I want to know how are rho gas and rho liquid selected, and whether I can do that both in my equilibrium case and in my non-equilibrium case. Okay? So is this clear what I'm trying to do? I have this field theory. I assume it gives me that. So I want to compute rho gas and rho liquid. So the first thing I will do is that if I have a system which is isotropic and there is no spontaneous breaking of symmetry, J is equal to 0. And because J is proportional to grad G, it means that G is uniform. And so I will call it G equal mu. Okay. And in particular, I can evaluate it at x gas and at x liquid. And so it's equal to J naught of x gas, and it's also equal to J naught of x liquid. Okay? So I have some constant which I don't know. Mu is unknown at this stage. But I know that there is a G naught has to be the same in both phases. So that's one condition. But I will need a second condition. I have two unknown, rho gas and rho liquid. And that's the one that's tough. And we will employ something which is called the Newton mapping to do that. And I will use it again in another context in flocking model, which is a standard method in nonlinear dynamics. So the first thing I do is I change the way I think about my problem. Right now I'm thinking about rho of x as a density profile. I will call rho z, and I will call x t, so that rho of x becomes z of t. And so now I'm looking at a trajectory. I have a dynamical system, and I'm looking at a trajectory that starts at a value rho gas, spend an infinite time there, and then shoot up and goes to another value, rho liquid. Let's call it instanton. And I can write down the equation. So the equation, I can read it here. I have G equal mu, and I'm in 1D, so I have mu equal f prime of z. Then I have minus c prime of z over 2 z dot square. So dx rho of x becomes z dot of t. Then I get minus c of z, z double prime, z double dot. And that's it. Okay. And so this is something that you like, because I can put the c on the other side. I get c of z, z double dot, equal minus c prime of z over 2 z star square. And then I have plus f prime of z minus mu. And this is classical mechanics. This is classical mechanics. That's mass times acceleration is equal minus the damping times the nonlinear friction minus the derivative of an effective potential. So this, I can write it as minus dz of v of z, with v of z being mu z minus f of z. Ooh. Okay, so good. Okay. So I'm trying to look for a trajectory that goes from one end to the other. I already have one condition, and I can look at what this condition means for my dynamical system. I see that I have mu that must be equal in both phases. And where is this? Where is this? Where is this? So in both phases, we know that G naught, which is f prime, is equal to mu. And so f prime minus mu is equal to 0. So the first condition that we had, which was G naught of x gas equal G naught of x liquid equal mu, means that v prime of x gas equal v prime of x liquid equals 0. And so these are critical points. These are fixed points of the potential. Critical point of the potential. And that makes sense. If you're doing classical mechanics and you have a trajectory like that, you know what you're doing. You're starting on top of a hill, you're staying there a long time, then you're falling down and going to the top of another hill and staying a long time there. So that makes sense. The problem is that we still don't know mu, so we don't know how to compute the position of these hills. And then there is another thing that you often do when you do this classical mechanics, is to look at integrals of motions. And now you can take this equation, which hopefully should be called 4, yes. And you can multiply 4 by z dot and integrate it. So if I do 4 times z dot, and I put all the derivatives to the left, and I integrate it, dt or dito? dt. Then what do I get? On the left, I have integral dt of c of z, z double dot times z dot, plus c prime of z times z dot cube over 3. And this is equal to the integral dt of z dot, which is dz over dt, times dv over dz. Or minus dv over dz. Minus dv over dz. And now there are two miracles which happen. The first one is that the right I can do it. So I can do this integral. And I will, I'm integrating from x gas to x liquid, x gas to x liquid. I have a total derivative. This is dv over dz, dz over dt, so that's dv over dt. So I get v of x gas minus v of x liquid. That's the difference in height between your two critical points. And then on the left, I'm very happy because this is the time derivative of z dot square over 2. And this is the time derivative of c of z, because I have c of z, z dot, times this z square over 2. So this is nothing but d over dt of c of z, z dot square over 2. I have to time integrate it, but I get it at the position of the extrema where z dot is 0. So this is 0.
The 3 was a 2, right?
Thank you. And so what I get is that v of x gas equal v of x liquid is equal to 0. So if I rewind my problem, what I'm given by nature is F, my free energy density. What I have to do is I have to find the value of mu such that this potential has an orbit that connects two critical points with the same energy. Okay? So how do you proceed? Okay. So you know, the two extrema with the same energy, with the same V. V prime equals 0? Well, okay, they could be saddles. What you say. Yeah, the two critical points. Sorry. With the same energy. Okay? Now, this is mathematics, and maybe you want a more physical intuition about what these things are. Yes?
It's mathematics, but also you had restricted, this whole thing works because you assume x to be dimension 1.
Yes, because I'm assuming macroscopic phase separation. So because I have macroscopic phase separation, I can just go through the interface, it becomes a 1D problem.
Okay, so that's the 1D.
Yes, that's where it's coming from. So it would be, even in D dimension, it's still true, this thing. But if I don't have macroscopic phase separation, I have to look at curvature problems, and it becomes harder. Yes. The big assumption that makes this work is that I'm doing the equilibrium case. Then we'll do the non-equilibrium case, and then it's trickier. Okay, any question? Okay, so that's the mathematical trick. Now, can we understand the physics of these equality? So let's recap. We have our first condition 1. We have that f prime of rho gas equal f prime of rho liquid equal mu. And now this second equality, we can look at the expression of mu, and the second equality is mu times z gas, so it's rho gas, minus f of rho gas is equal to mu rho liquid minus f of rho liquid. So there is a nice graphical way of plotting this. I was given a free energy. I want phase separation, so I want it to be non-concave. I have something like that. I'm looking for a value of mu and points rho gas and rho liquid such that the derivative is the same. And now my second equation, 2, I can rewrite it in a different way. 2, I can also write it as f of rho liquid minus f of rho gas equal mu, which is f prime of rho liquid or rho gas, times rho liquid minus rho gas. So the difference of values of my function is the derivative times the distance between the points. It means they have a tangent line. And so what I have to do is to find rho gas and rho liquid here, which are such that there is a common tangent to f of rho. And mu, the chemical potential, is this slope. There is a connection we can do. Okay, so this is how with field theory, ignoring everything about equilibrium thermodynamics, you find phase equilibria. But then if you remember your undergrad thermodynamics, you know that the same thing should be equivalent to having the same chemical potential and pressure in the two coexisting phases. So how can we connect these to that? Well, we have a free energy, or big F. Okay? So if we take a homogeneous system, at density rho naught, then we see that the free energy F is essentially the volume times F of rho naught. If the same is homogeneous, the gradient terms don't play a big role. So if I want the chemical potential, I have to compute the derivative of the free energy with respect to the particle number. Okay, rho naught is just the number of particles over the volume. So I see that I will have V F prime of rho naught times d rho naught over dn, which is 1 over V, which is F prime of rho naught, equal mu. So the equality of the slope here is the equality of chemical potential. Okay. The second observable in thermodynamics that is equal between coexisting phases is pressure. Pressure is minus the derivative of free energy with respect to volume, minus dF over dV. I get minus F of rho naught, minus V F prime of rho naught. And if I look at the derivative of rho naught with respect to V, I get minus rho naught over V. And so you see that what you get is minus F of rho naught plus rho naught F prime of rho naught, which is my condition 2. So my condition 1 is the equality of chemical potential, and my condition 2 here is the equality of pressure. So you can connect both your field theoretical derivation to the physics. Graphically, you can read the pressure here. This is minus P, the intersect with the axis. Okay, so this is equilibrium.
So you could have more than one such thing?
You could have more than, you mean more than one solution? Yeah, so I could have, something like that, for instance, and then I would have a second one, and then depending on where I'm in my phase diagram, I would see one or the other. Yeah, here I've looked at the simplest solution. Okay, so now what I want to do before the break is what happens if I don't have 2 lambda plus kappa prime equals 0. How do I generalize this phase equilibrium to a non-equilibrium setting? And then we'll go back to active particles tomorrow and see how this allows explaining the phase equilibrium in phase separating active matter. Are there questions on that?
I guess it's just P times some the volume, right?
No P is intensive, F of rho is intensive, so it should be fine. Yeah, no, it should be fine. That's the pressure. Okay.
I'm sorry,
Yeah.
I'm lost. Where did we use this 2 lambda plus k prime equals 0?
So just when we took the free energy, when we said that G was the functional derivative of the free energy, that's when we got a G which had this form, in which this coefficient and that coefficient were not independent, and they were coming from the free energy. Well, in general, by symmetry, they could be anything. And when you take this active matter model and you coarse grain them, you get something like that, but with kappa and lambda, which are arbitrary. And so that, yeah. Any other question? Okay. Okay. Up. So how do things change when you have when you don't have a free energy? So we still have essentially the same equation, but our equation 4, So equation 4 now becomes a bit different. It becomes, where is it? So my C is what I call kappa. So I get, kappa of Z times, let me do it with rho. Kappa of rho times dxx rho plus, and I get minus lambda of rho dx rho square equal g naught minus g naught of rho minus mu. I mean, we still have j equals 0, which still implies that g equal mu, so that g naught of rho gas equal j naught of rho liquid equal mu. So in a way, in this system, we do have a generalized thermodynamic chemical potential. The difference is that these terms are now generic. If we multiply this by dx rho and integrate, this will be a total derivative, we'll be happy, but this will not be 0 and we'll be very sad. So the question is, what do we find to replace the trick we had here that made this a derivative? The answer is that, here we multiplied by z dot and recognize the derivative, but we didn't have to. This was our choice. So we can maybe multiply by something else that can help us. And I'm sure that this is a trick that must be known by mathematicians. I just never found the name. But if you do, please tell me. So what we do is we say, OK, let's look for a function. We look for a function R of rho. And what we want is to be able to compute the integral of kappa of rho dxx rho minus lambda of rho dx rho square. And instead of having dx of rho, here I will put dx of R of rho. Dx. And this will be, by definition, the integral dx of j naught of rho minus mu times dx of R of rho. Okay? And we want this to be dx of something, so that we can compute it. And now, if we look at this equation, we can see that we have kappa r prime dx rho dxx rho dx rho minus lambda r prime dx rho cube. So I can divide by 2 and put a 2. This is the derivative of dx rho square over 2. So if this guy was the derivative of that guy with respect to rho, then we would have a total derivative. So if, if 2 lambda r prime is equal to minus d over d rho of kappa of r prime of rho, then this guy, then our bracket becomes dx of kappa r prime dx rho square over 2. We integrate between x gas and rho liquid, and we get 0. So this is r prime of rho. So these we can expand. We get minus kappa prime r prime minus kappa r double prime. To solve this, we see that we have to solve an ODE, which is kappa r double prime of rho is minus kappa plus, there should be a minus kappa prime plus 2 lambda times r prime. If we have solved this, then we know that the integral on the left-hand side becomes equal to 0. And if this we integrate with respect to r. So if we say that this is d5 with respect to dr, here we get dr with respect to d rho. This becomes, sorry, dv. This then becomes a total derivative, sorry, dx. And it becomes v of r liquid minus v of r gas. So essentially, what we are saying is our field theory is not the derivative of a free energy, but we are looking for a kind of integrand factor that we can put here, such that these gradient terms integrate out. Instead of looking just at the integral of these with respect to rho, as we did here when we integrated, no, okay, that was not here. Instead of integrating these with respect to rho, we have to integrate with respect to r, and then we get the equality of this potential. So let me summarize the recipe. And so let me first write the new conditions that we get.
So just to follow that,
Yes.
this integrating factor before, typical R was just rho.
Exactly. So when you're in the equilibrium case, 2 lambda plus kappa prime is 0. So essentially you get a linear function and yeah. So before it was just rho, and that's why we were looking at the derivative. And we can just generalize it using this kind of weird function. It's an ODE, so there is always a solution. You can show it's a one-to-one mapping, so everything seemed to be good. And so, okay, so here, if I look at my new potential, V of R, I have to integrate this guy, so I will call it phi of R minus mu, where d phi over dr is, I have to invert my relation, J naught of rho of R. And my two conditions are what? Mu is the same in both phases. So mu is the same in both phases. It's given by J naught. So we still have, okay, sorry, mu R. So we have mu equal J naught of rho gas equal J naught of rho liquid, which is also phi prime of R gas and equal to phi prime of rho liquid. And then we have our second condition that we get by integrating. We have V of R gas equal V of R liquid, which means we have this equality of our new pressure. Where is my V? It's up there. Where did I do it? It's here. So I get phi of R gas minus mu R gas equal phi of R liquid minus mu of R liquid. And so what you see is that this is nothing but a common tangent construction. Tangent construction on a generalized free energy, phi of R. So what is the recipe? One, you coarse grain your non-equilibrium model. Two, from there you determine, by doing a grain expansion, kappa of rho and lambda of rho. From there, you get this generalized variable R of rho by solving this ODE here. Three, you compute phi of R, which is the integral up to R dr of the local part, J naught of rho of R. And then you do a common tangent construction. On phi of R. So is it difficult? Depends. For what we call quorum sensing active particle, which are systems in which the speed at the microscopic level is defined as with this V naught of rho, so that we know the effective density-dependent speed. We can do all that, and I'll show you that tomorrow probably. And it works like a charm, and you can get without any fitting parameter analytically the phase diagram. It works very well, matches simulation very well. Pairwise forces active particles that I told you at the beginning, it's much harder. Getting the local part, the G0 part, is relatively easy. We did that a long time ago. The gradient terms are much harder to do, and it's been done by Ahmad Omar, who's an assistant prof in Berkeley, and he did it in 3D and for disordered 2D, because the monodispersed 2D is somewhat harder, and it seems to be working very well. So I will finish on this rather dry piece of mathematics, and tomorrow I'll show you applications of that and how you can indeed predict the phase diagram of this particle-based model, and then I will very briefly discuss application to bacterial pattern formation, so that you see that it's not just something that we do in a computer, but it's also relevant to experiments, and then we'll turn to collective motion. Thanks very much for your attention, and if you have any questions, don't hesitate.
Thank you very much, Julien. Are there any questions?
So this trick that you use for the function R, can you generalize when you don't have scalar theory? But you have
So you can work out conditions when you have multiple fields, and you can, but not always. Even with a scalar field, if you had higher order derivative, same thing, you can, but with second order derivative, it's always. But in higher dimensions, there is a subset of non-income systems that you can solve like that, but not all of them, unfortunately. Yes.
So this simplification to one dimension depended on assuming that it has a low curvature droplet.
It depends on the fact that I can do a gradient expansion, that my current don't have crazy non-local dependencies, and that I have macroscopic phase separation, so that I can just look at an interface, I go on an interface and I'm fine.
Is there a way to self-consistently tell after the fact if that's a reasonable assumption or not, maybe on the slope?
So what you can do afterwards is you can go back to your full PD and do the linear stability of the phase separated system you've seen. So for instance, one thing that you can check is whether when you have two droplets of different size, the small one evaporates and the big one grows, which will drive you towards macroscopic phase separation or not. So that's called Oswald ripening. And it's been shown that you have some active systems in which you get reverse Oswald ripening. So instead of having the big droplet that grows and the small that evaporates, they get to the same size. Cesare Nardini and Mike Cates did that. And so for these models, then you would not get to the macroscopic phase separation. So you would have corrections which scale as 1 over the system size. One comment, with these gradient terms in your free energy, you can define a surface tension, a thermodynamic surface tension, that allows you to correct finite size corrections to the coexisting densities. You can do it also with these R variables. So you have a surface tension, and essentially in systems that do Oswald ripening, the corrections go in one direction, and in systems that do reverse Oswald ripening, they go in the other direction. So you have a litmus test to tell you, I take a simulation, I have my theory, I can tell you, what will be happening. But this is just testing one scenario. You could have other, transverse instabilities and stuff like that. So, and then doing the linear stability analysis on nonlinear profile is doable numerically, but analytically it's very difficult. Any other question?
Yes. So related to what you say, that so in the equilibrium case, this is also a starting point. This analysis to study nucleation theory.
Yes.
So can you generalize and then put times and noise?
Yes. People have done that. Again, Cesare and Mike have done that. They have done nucleation theory for active model B and B+. Start using these R variables. Somehow these R variables that they introduced for phase separation, they turned out to be useful in a bunch of other contexts. And I don't think that anybody has a really clear physical understanding of these variables. For now, it's a nice trick, but
must mean something.
It must mean something, and it must be known also, because it's not rocket science, but we didn't find it anywhere.
Okay, so maybe it's time to stop there, and thanks again, Julien.
Thank you.